Right, my name is Francois Zinseling. I'm an engineer by profession, qualified from Pretoria University somewhere in the late 80s, early 90s. And physics is and has been recently a great hobby of mine. It's taken a lot of my time, and I hope to share some result with you tonight. When we talk about gravity, we need to maybe discuss what is gravity first. So technically, we would say that anything that has mass adds to gravity and is a resultant upon the acts of gravity. So if we say anything with mass, anything that you can think of that has a mass, and I've shown here hydrogen, but electron, hydrogen, proton, neutron, as small as you can get, and as large as you can get, of course, suns, stars, and black holes. If any mass is subject to gravity, what you see on the screen, we've got a hydrogen atom. So this is just an example of a mass, and it is a very, very tiny mass. How do we know that that mass would also act gravity? So first of all, we would take that hydrogen, put it in a vacuum, and drop it. If it falls, like on the right-hand side of the screen, typical to like a tennis ball would fall, then we know that that mass is also subject to gravity. If the mass is subject to gravity, then it also means it causes gravity. And what we have at the bottom of the page, you would have two little masses. There would be a gravitational attraction between them. So these have been measured for really, really tiny masses. So it does exist and it is real. That same mass that is attracted by gravity that we show on the right-hand side here is also the same mass that would accelerate with an acceleration at A if we subject it to a known force F. So this one on the left is called inertial mass, where the one on the right is called gravitational mass. These two are exactly the same, although they are subjected to different scenarios here. If we then say that every little mass adds to the gravity, it's going to get complicated very quickly. If we look, for instance, here we have a neon atom on the left and on the right. And we say, okay, let's see what the effect is of gravity of one of the electrons of the neon atom. So there are 10 electrons, and from that one electron to the other neon atom, we've got all those connections that are supposed to be gravity connections. How does that happen? Well, we don't know. And it gets even more complicated because it has to enact on its own partners as well. The electrons in the atom, its own nucleus, and that nucleus consists of 10 protons and 10 neutrons, whereas each one has to interact with each other gravitationally. You would agree that this is a very, very complicated mechanism, which if we had to try and describe this mathematically, we would run into trouble very soon. We also define that gravity moves at the speed of light. So I've written it up there saying speed of light, speed of gravity. What you'll see later is that it's really the same thing. When the gravitational waves were first detected by LIGO, at the very same time, an X-ray was detected by the Chandra Observatory within a fraction of a second of the detection of the gravitational wave. Now, bearing in mind that this signal traveled from a distant galaxy, not even from within our own galaxy, and those signals corresponded to a very large degree, giving us a confirmation that X-rays, being light or electromagnetic radiation, arriving at the same time as the gravitational waves, tells us that gravity moves at the speed of light. So this is what we know about gravity. Now let's say we now know that the gravity moves at the speed of light, and we try, and some of you may have heard of a graviton. Let's try and enact a gravity on, let's say, between the sun and the earth. So my mouse always gets lost, but so first of all, here is, let's say you could be put into a suit. You go to the surface of the sun or the center of the sun, and your job is to enact gravity onto the earth. So first of all, you would look and say, well, where's the earth? And you say, okay, well, there is the earth. Let's send a photon to go and cause gravity. But you would be wrong, of course, because you are seeing the earth. Remember, the light travels between sun and earth is about 8 minutes. So you're seeing the earth where it was 8 minutes ago. So in reality, the earth is now here. If you send your photon there, you would miss the earth completely. Let's say you were smarter than that. And you say, well, I knew this light took 8 minutes to reach me, so I will send my photon here so that it could enact gravity onto the earth. You would still be wrong, because in the next 8 minutes that it takes your photon to reach that spot, the earth has moved over there. So you now have to be twice as smart to send your photon to this position if you are launching it from the surface or the center of the sun. So to expect the sun or a photon to be smart might be a lot to ask. Twice as smart, twice to ask. It's maybe similar to saying we see because we project from our eyes. It is a little bit borders on ridiculous. Yet Newton got it right. Newton's equation predicts exactly where the mass is. How does he know? How does Newton then, Newton didn't even know of photons at the time. How did he know to make his equation, and how does it work while gravity is at the speed of light? How does Newton's equation still work? Well, we will find that out. Let's look at what could possibly cause gravity. There are obviously many things. I've just taken a few silly examples. We could have ropes. In school, we learned that gravity is an attractive force like a rope pulling from one to the other. It also tells you that the force on one equals the force on the other, which you would typically get if you had a rope tied to both sides. That pun there has got nothing to do with string theory. Really not. An alternative would be to try and create a pull force with photons. This is really a thing. Hung Lee et al. Have achieved what they call photon pinches to create an attractive force using gravitational waves. However, this lot takes a lot of energy to just move a small mass. So to say that this could be a representation of gravity or a gravitational attraction is also a little bit of a long stretch. Let's look at a vacuum. If you were a person sitting inside that can, and you could prevent your ears from popping and your eyes from popping out, and someone pulled all the air out of the can, you would see the sides of the can moving towards you or towards each other, and you would think that there is an invisible force attracting the sides of the can together. We all know that the vacuum crushing a can is really the pressure on the outside of the can that's higher, that's pushing the can inwards when the inside pressure is getting lower. I want you to keep hold of that image because we're going to use that concept to construct our gravity. We need three properties of light to build gravity from electromagnetic matter, electromagnetic waves. First of all, we need to show that electromagnetic waves experiences transparency of matter. So in other words, it can move through matter. We will talk about all of these just now. We also need to show that photons can transfer momentum. We also need to show that photons are and can be absorbed partially or wholly into matter. None of these are fidgets of my imagination. They are real physics items. Let's look at transparency. On the left, for instance, is just an example. I'm not saying neutrinos are photons, and I'm not trying to imply. I'm just wanting you to get the analogy here, that at every second, 100 trillion neutrinos pass through our body, and that is just from the sun. The other number that comes up is 10 billion per second through the nail of your thumb. So that is the quantity. Now, we can't feel that. We don't know that that is happening. That is, again, an image that I want you to take away or take forward with you. In other effects, transparency is not unknown to us. We know that light can go through glass, even though that is a special case of transparency, but it is a good enough example for what we are trying to do. We know that a human body is partly transparent to X-rays. Now, X-rays are a higher frequency than visible light, substantially higher, and the image you would get on a receptor would be an image of the light that was not absorbed. In other words, the dark image you see is created by the photons that went through the hand, and the light part is where the photons didn't get through. They got absorbed by the bones. So the non-bone part is mostly transparent to X-rays. So that's the first one. Secondly, here's a bit of physics and a bit of maths. We need to show that photons can transfer momentum. Again, not a new thing. We know that the momentum of a photon is equal to its energy divided by the speed of light. If we were to take a single photon and send it towards a solar sail, if the photon was reflected by the sail, in this case a very reflective photon, a reflective sail, we would get twice the momentum onto the sail. If you think about it for a second, 2 times momentum to the right into the sail and minus momentum where the photon gets reflected. Still leaves you with +1 momentum. If the photon gets absorbed completely, the +1 momentum goes into the sail and it will push the sail in the direction that the photon was moving. In the case of transparent matter, it's a little bit different. Photon slows down, for instance, visible light through glass or through water, slows down in the transparent medium while it is in the medium. Once it's out the other side, it resumes its velocity as it would in whatever that medium is, being it air, vacuum. So while it is in the glass, being slowed, it is transferring momentum to the glass. The fact that it is being slowed, the balance of the momentum is effectively being given to the glass, and it is pushing on the glass while the photon is in the glass. Now, that is currently a very big subject of research. This image that I show you is from one of the references that I also use in my paper. Then we need to show that light can be absorbed. Light, being an electromagnetic wave, can definitely be absorbed. Every electromagnetic wave will act like, will react to coming into contact with matter according to the graph that you see on your left-hand side. This works for your Wi-Fi signal that you're trying to send through a wall, or a radio transmitter that you have on top of a hill that's sending it from one town to another. That loss occurs over a distance and depending on the matter that is in there. All of these parameters here determine the amount of loss over what amount of distance. I do need to make one clarification here, which will suit our needs. There are 2 possibilities of absorption. And I call the one 10 in, I used to call it 10 in, 9 out, but it's 10 in less than 10 out. In other words, some of the photons are completely absorbed. This would be typical in maybe an X-ray, where some photons are absorbed into your bones, the rest are let through, and you're able to make an image. But the point to take here is that not all the photons make it out the other side. Then there's an alternative way where we have 10 in and 10 out. But in their transit, a little bit of energy is lost. Now, we can't just make energy disappear. So there has to be, sorry, I think I have an outdated PowerPoint, but there has to be a little bit of energy that escapes because we can't just make energy disappear. But if you think, for instance, where we had the glass and the photon was moving through it, if that glass actually moved a slight bit, then work was done. So the photon coming out the other side has to come out with less energy. In other words, it did some work, some energy was absorbed in the glass, even though it is stopped again afterwards, that energy cannot go back into the photon. So it comes back out with a little bit less energy. We're going to go with this one because it works for what I'm trying to present. When we look at Newton and Einstein's equations, both of them have the gravitational constant G. That is the value of G given by the National Institute of Standards. And Newton's equation briefly looks like this. Einstein's equation briefly looks like this. Einstein's equation obviously a lot more complicated even than it looks there. When we look at what Newton is trying to tell us, what we can get from this is that we have two masses in the equation and we have a distance, and the force of attraction between them is based on a constant G multiplied by the factor of the two masses divided by the square of the distance. So we know that if we have more mass, we have more gravity. We know if we have less distance, we have more gravity. That still doesn't tell us exactly how it happens. It just tells us how it might react if we change some of the components. In the case of Einstein, some of the interpretations that were given, and you may have heard this, is that mass tells space how to move. In other words, it bends space. And then space tells mass how to move. In other words, mass will follow the curve of space. You may have heard this somewhere else. History of gravity. Since Newton in 1687, when he published his Principia, there have been numerous attempts at what I am presenting to you here now. And it's also mostly known as push gravity, which became known by Lesage from the time of Lesage. The first person to do it, though, was 1690 Fatio, who happened to be a close friend of Newton at the time, tried to convince Newton that gravity really had to happen because of a push, not a pull. Even though the effect appears to be a pull, remember sitting inside the vacuum can? The only real way it could happen was because of pushing forces. Newton did consider it for a short while, but because they couldn't find a solution, he discarded it. Fatio was quite broken by this. In 1748 was the first time a paper was published, and that was by Lesage, and it was called push gravity. The theory was called push gravity. It was met with a lot of resistance, and justifiably so. So first of all, I can tell you that neither Newton, Fatio, or Lesage knew of photons at the time. They didn't even know of atoms. And of course, they didn't know about the spacing between atoms or the low mass of atoms. So the whole idea that they had, in my opinion, was quite remarkable, but they were doomed to failure because they didn't have the tools to make it work. Of course, we know Einstein's theory of general relativity is the pinnacle of gravitational theory as we do know today. We do not question Einstein. A brief image on push gravity. This is an image taken from the original publication of Lesage, which shows, and this is where it's going to become really tricky to try and explain to you what this flux is all about. And it is really all about the flux. Imagine coming from all directions. So now I'm talking Lesage, right? I'm not talking my paper yet. Imagine coming from all directions, tiny, 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 tiny particles the size of grains of dust, but so small that they could literally fly through atoms. Again, keeping in mind Lesage didn't know about atoms. But the image shows that from the left and right is a lot coming, and not so many make it through the first ball, and even less make it through the second ball. What this effectively does, it creates a slight vacuum between the two balls, which will push them together. Now, this is as far as this theory works. After this, it becomes hugely problematic, and that itself will be a talk on its own. So I'm not going to be going into that too much. I would like to introduce you to the omnidirectional photon flux. Now that we know about photons and we know about atoms, we can make this work. Think now about a mass, in this case on your screen, a spherical mass, that has shown you in 2D, but really in 3D, there are photons going into it from all directions. And because it's transparent, remember our other condition, because it is transparent, we have photons going out in all directions. There's no interaction like refraction or bending of light experienced here. That is not part of the action. So this would be like visible light going through a clear glass. It is not disturbed, it is not transformed, it is not bent or anything like through a prism. It just goes straight through. If it goes in that side, it will come straight out the other side. Condition is, it will slow while it's in the mass. It will transfer some momentum while it is in the mass. For me to make this work, and this points a little bit at the paper, what I do is I take everything on the left. In other words, think of a cushion of needles, a ball that you filled with needles all around, 3D. You cut it in half, and all the needles you have on the left-hand side, each one of them, if you look at it from side on, has a small portion pointing to the right. Some of them will have a small component, some put right there will have a large component, but everyone has what we call here the X component. We add up all of these X components of photons, and we add up all the X components of photons on the other side. Because we know the mass is not being pushed around, we know that the components are equal in both directions. In other words, all of these photons together are not pushing this mass in any direction. It is standing still as if there are no photons, but it is because they are equal. Now we come back to our atoms. If we look again at the effect of our electron on its neighboring atom, the question is now, that effect that that electron had on that one, was it pulling, or is there some pushing involved here? We've shown that if there's a pulling required, then we need a mechanism that connects from here to there, which becomes problematic very, very quickly. So is it possible that there is a pushing from that side? And why does it push to the middle of that? We will find that out soon. Let's compare, for instance, the two masses on the screen. We have one large mass. Let's say this is the Earth. We call that big M, and we have the Moon, which we call small m. If we had push forces from the side, where now look at this carefully. This is small m. So there's a force on the big mass caused by the small mass. In other words, this F is caused by that M. And we have a big M that causes a force on this side, which pushes these two masses together. If we took that force and we added in the middle in our rope scenario, we would have what we understand as gravity. But how would we know the difference? If every atom in this mass is being pushed towards that mass, how will you know the difference whether you are pushing or pulling? You wouldn't. Let's go back to our absorption curve. The absorption curve is typical for an electromagnetic spectrum. You have an incident strength of your flux, we'll call it flux. I've heard people have struggled with a bit with the term flux, so I'll just define flux as, in this case, a measure of the flow of energy. I don't know how much that helps, but let's think about it like that. So there's a measure of the flow of energy going in on the left. Some of it gets absorbed, and it goes out on the other side, slightly weaker. The curve here is defined by this equation. So the absorbed part would be that minus that, and it would look like this equation. Don't worry too much about that. Or please, if anyone does worry about that, I would love for you to have a look at my paper and engage. Now we look again at our 10 in, 9 out, and we know that some of this will be absorbed and go out the other side. But we look at this energy, and we now know that high energy goes in, slightly less energy goes out. We're not going to use the first one, but yes, we will use the second one. Definitely something went wrong with my PowerPoint. There's the photon that was the subtraction of that minus that. We will count this to escape as heat. So first question that you may already have is, well, if this one's pushing and that one's going to push less, then this should make up the difference, so there should really be no difference. What you do need to realize is that there's a factor which is called the refraction index, typically, which is higher for high frequency and lower for low frequency. So even though we said earlier the momentum of a high frequency is higher than that of a low frequency, the actual amount of pushing of a high frequency is again higher than that of a low frequency. So in this case, when this escapes as a very low frequency, we discard that as having any component of pushing or pulling. We continue with our scenario of 10 photons in and 10 photons out, where the photons going out go out with slightly less energy, and we ignore the energy that was absorbed inside the mass. If we had no absorption in a mass, it would look like this. All the photons would go in one side and out the other side with equal amount. And if we were trying to construct gravity here, we would have a problem, because we may be pushing, where's my mouse? We might be pushing down here and create gravity, but we're also going to be pushing out on the other side. So whatever we pushed in, we push out, and things just won't work. If we do have a slight amount of absorption, though, we would get this effect where, and this is not to scale, this is just a different picture, where we have one amount of energy of photon going in, and here the representation is not the wavelength of the photon, but it's, let's say, a vectors showing the strength of the photon. So a strong photon goes in, a weaker photon goes out, like we have there. And this happens right throughout. Again, picture this in your mind in a 3D scenario. If we take this now at any point in space, high energy going in, less energy going out, we can equate that to looking like this, where we have a net inflow of energy into the mass. So we are almost there to create what is needed to explain gravity. Let's go back. Sorry, let me just show this again. We have here the mass, which has this imbalance of flux around it, which causes a net pressure inwards towards the mass. This is one mass only, right? So we haven't brought anything else in vicinity of it yet. And we've only dealt with absorption at this point. So in other words, the flux that goes through any mass, through you and me right now, a small fraction of it is absorbed and slightly less go out on the other side. So a very big mass like the Earth would have what I call an imbalance around it. Now you bring another mass into the vicinity of it, and it is now being affected by that imbalance. And this imbalance will transfer momentum onto this mass. In other words, it will push it towards that mass. So if we had, first of all, this big M was this one with the imbalance around it. Here's the imbalance, and we brought another mass in the vicinity. This mass will be affected based on the surface area that the flux goes through, multiplied by the average path length, in other words, the whole volume of the mass. And the more density there is, the more this will interact. In other words, in total, the more mass there is, the more interaction there is. This only shows the inaction in one direction, of course. The same applies in the opposite direction, where this mass would have an imbalance around there and pull this one or push this one closer to it, whichever terminology you prefer. From this, we can take, for instance, for a spherical mass, because we have a symmetric flux through a spherical mass, we count on the flux being equal strength from all directions, because we are in a balanced flux. We can now invoke what we call a Gaussian sphere, for those who have knowledge of maths and physics, which tells us that for a spherical object in the middle, the strength of this imbalance, if we want to keep calling that, will drop off at the rate of 1 over r squared. This is already known. If you know about, and here's another example of flux, is if you've worked with solar panels, you'll know that the solar flux on Earth is measured at around about 30 watts per square meters. And that solar flux drops off from the surface of the sun at this rate. That is how we can calculate what the strength of the sun is, by measuring the flux on a square meter of Earth. This 1 over r squared is very important. Obviously, this applies to spherical mass. If we had an odd-shaped mass in there, we would have an odd-shaped gravity field around it. That is not new or a revelation. We know that, for instance, a long bar has more gravity out the ends of it than it has out the sides of it. I'm explaining this badly. Let me move on. From what we've done so far, an equation is derived. So here, this is not correct. This is actually equation 56 in the actual paper. So there's a lot of preceding work that happens before this. But what I want you to see here is that we have F equals this number times m over r squared. This was not just derived ad hoc. It is done step by step and in much detail in the paper. I do beg anyone possible to go and verify that and engage with me if possible. Compare that to the Newton's equation we had earlier, where we say that the force F between two masses equals G, the gravitational constant, times mass over r squared. There we have mass over r squared. But we have this weird number here now, which contains our flux absorption, the flux intensity, the strength of the flux, and the flux interaction, or the pushing part of the flux. So this was two of our original premises, was that some absorption must happen and that momentum can be transferred. Now, neither of these are inventions that I've just conjured. These are known principles of electromagnetic waves. The only thing I am conjuring here is the flux, that this is something we do not know about, but here, from the premise of its existence, I have derived Newton's equation. I'd like to pause for a moment here and just point out, or just say, and this is also because of some reactions that I've had, is I'm not trying to reinvent gravity here. The derivation of Newton was a marvelous moment for me, but I was not trying to define a new gravity. I was not trying to fix gravity or change gravity or anything. I was just hoping to explain gravity, because from the moment I had seen Lesarge's papers, I had a very strong suspicion that this had to be correct. The result, though, was here I come out and now I say that there is this flux that none of us know about, but if it exists, this is what the equation would look like. The big thing to take away here, and this is the first kick on the shin, is that the gravitational constant G is not a constant. Is it a problem? No, it isn't. I'll tell you now why. From this premise that we've taken that there exists an omnidirectional photon flux. In other words, a flux of electromagnetic radiation of such high frequency that ordinary matter is completely transparent to it. I do need to go back. Something that I skipped over here. One of the big reasons why this is discarded. If I say that the flux is of such high frequency that ordinary matter is transparent to it. In other words, I'm predicting that this frequency is way, way, way above X-rays and way, way, way above gamma rays, because we already know that the higher the frequency, the smaller the cross-section and the more waves get through atoms. So the prediction is that it is such a high frequency that it no longer interacts with matter at all like an X-ray would. In other words, a whole photon would not get absorbed. It does not get absorbed. And the reason why I could say that confidently is that we know that if an X-ray photon is absorbed, it has the ability to do great harm in, for instance, a human body. Here I'm predicting a much, much, much higher energy for the photon flux. If one of those photons were to be absorbed in me, I would be boiling. And although it's hot tonight, I'm not blowing up. So that's why we stick with this method of absorption. Sorry for the hijack. Back to the premise. What we have shown so far, we've shown that gravity can exist as a result of electromagnetic radiation. Push photons, push gravity, whatever you want to call that. As short as my talk may be, the paper does explain it in more detail. There's also another introductory video along similar lines of this one with low mathematical content. We have shown that inertial and gravitational mass is unified. This is because effectively in the flux, mass is defined by your movement in the flux. We have shown Newton's instant action at a distance. How? Go back again. Here. When mass m created the imbalance of flux around it with no other mass in its vicinity, all of this happened at the speed of light. Photon goes in, photon goes out, and this imbalance around here and this in this space here is updated at the speed of light. If this mass will be moving this in one direction or the other, or if it were to be accumulating mass for some reason, this area here would be updated at the speed of light. The imbalance there would change at the speed of light. In other words, this mass sitting or arriving close to this mass, which is a difficult way to predict because gravity has such a long reach. But while this mass is moving, it is where the imbalance is already there. If you can understand that, the imbalance around this mass was created at the speed of light. So the movement of this mass, in other words, for example, the movement of the moon around the Earth is much, much, much slower than the speed of light. And so is the movement of the Earth around the sun, much, much lower than the speed of light. So when the Earth moves forward in its path, it does not have to wait for a photon to arrive from the sun. It's moving into an imbalance that is already there. That is how Newton's instant action at a distance can be explained. We have shown the 1 over r squared for spherical masses. And here, although I've taken great care to point out that I do not have any argument with Newton nor Einstein, unfortunately, this rules out modified Newtonian dynamics. Modified Newtonian dynamics, for those who don't know, predict a different drop-off of gravity other than 1 over r squared. I did not set out to oppose Mond, it just happened. Understanding the flux gives us an understanding of spatial and general relativity. We can now understand that our motion in this flux is our reference frame. That will give rise to all of the funnies that we have experienced from special relativity. And I must say here that I was a great opponent for a long time against special relativity. I am now probably, no, I'm not anything much, but I really understand it well now. We can also say that the gradient of flux is the curvature of space, which would be the equivalent of bent space in Newton's general relativity. We have explained why, and this is a big thing for people who try and measure G. There's a big concern that we can measure the electromagnetic attraction of charged particles up to, I don't know how many precisions of decibels, but with G we just cannot get it right. The same experiment would give different results every time, and G cannot be pinned down. Although we have a very, very good accurate measure of G, it should be a lot better. Anyone who knows about the measurements of G or the problems of the measurements of G will now realize it is because G is not a constant. And even though the flux may not vary a lot in our environment, any slight variation will cause a variation in G, and your G measurement will be affected badly. We can now, though, predict that larger masses would give a different G, different materials would give a different G. So that is something that we can go and test. Because G is in part a measure of the flux and also of the interaction between the two masses. From this hypothesis, apart from what is already jumped out, which I am really personally ecstatic about, I do need to get some high-level verification to take me, I think, to the next level on this. But even as it is, this hypothesis is not a dead end, and it already comes with new predictions. And I don't want to, yes, I will give away too much, but I just need to say that these are speculations, but I would say in the same sentence that speculations that I'm very excited about. In the first case, that this flux, the more that you think about it, the more you are going to love it. The flux would be the origin of space and time. Any message would be carried on this flux between one point and another, and the flux then becomes the agent of causality. we are already working towards a solution for dark matter with a variable G. And we don't need to invent an ad hoc G variation. It's very well explained why G would change, for instance, in a galactic disk. And this is the big one that if you haven't fallen off your chair laughing yet, then this is the one. Cautiously excited, again, speculation. The flux is going to unify gravity with a strong force. I will not say too much more about that. Of course, there's much more to do. We do need to present a time-dependent solution. What I've derived here as Newton's equation is not generally accepted in physics terms as anything good, because it does not show a time-dependent or a relativistic effect. However, from the understanding of it, this is now possible. We can start to explain gravitational redshifting. Think back about our blue photon, red photon going through the mass. This is actually exactly that. Now, I'm just saying this in words, or as Feynman would say, I'm just sitting here waving arms. Of course, this all needs to be put into mathematical terms and presented properly. With the gravitational redshifting, we would be able to show how clocks slow down in a gravitational field. Dare I say, because this solution defines gravity as a result of the electromagnetic spectrum, quantum gravity is now inevitable. No, it's not in my reach. I don't think I have the mathematical capability for that, but there are others who surely do. We do have a little bit to say about fusion, and it's not likely going to be good news, but there is something about that as well. So these are just predictions that would be coming out in the near future. I thank you very much.